So good morning, everyone. Welcome back to Math 115. So today we are reviewing for the exam, which is tomorrow. So exam is tomorrow in our usual Wednesday classroom. Lawson and Randall, where are you? Put you in the attendance. Okay. Where was I? Oh yes, the exam, which is tomorrow, will be proctored by somebody who's not me. So don't be surprised when I'm not there. Okay, we're gonna have a proctor.
Is the same person? Is the same guy as last time?
Different guy.
Okay.
Why?
He was little. Because everybody was coughing, but everybody was getting sick, and he was like, ugh. And I was like, he was like making fun of us. And then
Really?
I don't remember who it was, but somebody asked him if something about the exam. He goes, "You can leave now for all I care." I was like, okay. It was a little bit intense. Yeah. Especially for our first exam.
I'm gonna tell him you said that.
Okay. I mean, I'll be tell it to his face.
I'm gonna say Lauren Holland from my class
He's gonna be like,
said you were unfriendly.
He's gonna her number. Have fun. He's gonna be like, who's that?
That's funny. No, it'll be somebody probably significantly more friendly.
I mean, he looks friendly, but you just get one asking.
That guy just has very little patience for undergrads, in my experience.
Well, that fits his description.
Anyways, so it's going to be proctored by somebody, not me, because somebody owes me some coverage, and I don't want to wake up early. So I'm gonna sleep in tomorrow while you all take the exam. I have to conserve my energy to grade the exams. There's like 45 of you, and I have to.
I feel like you're literally like, I could see you like grading exams being like.
Okay, that's kind of like startlingly accurate. That's sometimes.
He's like, that's stupid. I feel like it could be like.
No, it's usually.
You also
No,
know
it's.
exactly like you know exactly who goes to office hours. So I feel like if someone did it and they got something wrong and we like went over, you'd be like.
No, it's usually. It's not like I'm disappointed. It's just like oh, I know they're better than this, and like it's probably just the pressure or something like that, you know.
You need to be like, go to office hours. Like, right on the top of the exam.
I feel like you've definitely done that before.
I have. Okay. Anyways, we're getting off track. We want to use our time to review today. So the exam is tomorrow, 8:30 a.m. Close at 4:50. I'm not going to be there, but a proctor will be there to do the exam. You can ask him any questions that you want. He'll be able to answer your questions. And the sections which are relevant for the exam are, of course, section 3.2 up to 4.6. So everything that we had homework on between there and there is going to be fair game for the exam. The exam questions are pulled from these sections. I have one question pulled from each of the homeworks, 3.2, 3.3, 3.4, 4.1, 2, 3, 4, 5, and 6. If I counted right, that's 9 questions, like usual, 3 pages, 3 questions per page, and a bonus at the end for plus 3 points.
10 points.
No.
5 points.
No.
7.
5 points would be like
0 points.
unreasonable. It's already like 10% of your grade is 3 points. So
How about 4?
no. Stop nickeling and diming me.
2 points for writing a human script.
Okay, that's the exam. I'm also gonna have additional office hours. Actually, not additional, just regular office hours today in LeConte 109. I have the room reserved so that I can use the projector, and I will record those office hours, and I will post them onto my YouTube channel. I'm also going to post this review onto my YouTube channel if you want to watch it as well. If you can't go to those office hours, but you want some one-on-one instruction, go to the tutoring center. It's open today from 10 a.m. to 4 p.m. Okay? All right. So that's all I want to say about the exam, unless, are there any administrative questions about the exam or otherwise? Okay, doesn't seem like there are, so let's review. as always, if anyone has any questions, then feel free to ask immediately. But I thought maybe what I would do is just remind you quickly of what we learned in those sections, and then maybe you will be more informed about what you don't remember. So, compound interest is not relevant. Okay, 3.2, here it is. Okay, so we learned about logarithms. Okay, so we learned about converting between logarithmic form and exponential form. That's very important, and it's also very important to understand the fact that these functions will be inverses of one another. Okay, so we can plug one into the other in order to undo what a logarithm does. We plug it into an exponential. To undo what an exponential does, we plug it into a logarithm. So we learned how to do some logarithms when it's easy to guess kind of like what is the power that we need in order to accomplish that. And we also learned a bunch of properties. So we learned, okay, these are just basic properties of logs. These aren't even the important log properties. But these are ones like, okay, if you plug an exponential into a log, it undoes whatever the exponential had done. Also, the domain and range of logarithmic functions. Well, the domain and range are going to be the reverse of the domain and range for an exponential. So as long as you remember the domain and range of an exponential, which the domain is all real numbers, the range would be 0 to infinity, right? So that's going to be, if you flip that, the domain of a logarithm will be from 0 to infinity, and the range will be all real numbers, okay? Then we learned about the graph. So the thing about the graph with logarithms is that there are 2 points which it always goes through. We learned 2 points which the exponential function always goes through, namely 0, 1, and 1a. So the logarithm is going to go through 2 points which are not 0, 1, but 1, 0, and not 1a, but a1. Okay, so those are the 2 points which will always be on the graph of log a of x. Any questions so far? Okay, for now, I'm just going to keep speeding through and give you a quick overview of everything, and then we'll get into more detailed questions later on. Okay, so then we learned about natural log. That's just log with base e. We learned about the change of base formula, which allows us to compute a log with a, using natural logs. We also learned about section 3.3 where we learned the log rules, okay? Product rule, quotient rule, and the power rule, which the power rule was the most important rule. Why was the power rule so important for logarithms? Why did I say that was the most important one? Yeah, why is that so useful? Exactly. We like to be able to get the exponent out, because if the exponent is, say, x, and we're supposed to solve for x, we have to get it out of the logarithm, right? We have to get it out of the logarithm. So we pull it out, and then we just get rid of the remaining logarithm by like dividing both sides by log a of m, right? And then we would have r by itself. Okay, so this is really important for solving logarithmic equations. Okay, so we need to know how to use these rules to do 2 things. We need to know how to go from a single logarithm and expand fully. What do I mean by expand fully? I mean that your final answer should have just logarithms with a single variable inside, okay? So we need to get rid of any like division or multiplication, and also any powers. The powers must come out when we are doing expanding. When we're doing combining, we want to take any number of logarithms and combine them all into a single logarithm using those rules. Okay, so the rules work in both directions. You can go from a quotient to a difference, and you can go from a difference to a quotient. And whether we're combining or expanding, we're going to use that rule in one direction or the other. Okay, then we learned about half-life. Okay, oh, actually, we didn't learn about we had learned about half-life already, hadn't we? Okay, maybe not. Anyways, you can use logarithms, of course, to solve for something which is in the exponent of a half-life problem, right? If you want to get k or t by itself, you just have to use logarithms to get it out of the power. All right. Then we had exponential and logarithmic equations and inequalities. Actually, we didn't really do any inequalities, did we? We skipped that. So solving equations, what do? When the thing that we want is inside the exponent, what do? When the thing that I want is in the exponent and I need to get it by itself, we should have a knee-jerk reaction to use the power rule for logs, which means I should take both sides of this equation. Well, okay, this one, I guess you don't need to do that because, okay, I failed to look ahead. Of course, if they have the same base, then you can try to do this kind of manipulation where you set the powers equal to one another, right? But otherwise, what would you do? We would do log of this side and log of this side, right? And then we'd take the x out and divide both sides by log 25 in order to have x by itself. So the knee-jerk reaction when the thing you want is in the exponent is to use logarithms. So this is a better example of that. Except what do I have to do if I use logs? The first thing I have to do is isolate that exponential, right? So if it's attached to like a 5 here, I have to divide both sides by 5 first, right? And then use logarithms at this stage, right? Then we use the logarithm, we pull out the power, divide both sides by the log, okay? Divide both sides by the log, that's how we got this equation, x minus 3 is equal to this fraction, and then we just add 3 to both sides to get x by itself. So that's an example of solving equations using logs. Okay, and here's a useful example of a really tricky problem when not only is the base different, we also have polynomial powers for each one. So how did we solve that one? Well, for this one, let's go through it slowly. I took the natural log on both sides because the thing that I want is in the exponent. So I just use logs immediately. And then what comes out is the power 2x minus 3 on this side, and then we have ln 5, right? And then x plus 1 here, and ln 3. Okay, so then what did we do? Well, our goal is to get x by itself. And this is a really nice problem which will test whether or not you understand the concept that natural log of 5 is just a number. Okay, it's just a number. And natural log of 3 is just a number, right? So what would I do? I think everyone in this class would feel extremely confident solving this equation. How would I solve this equation? I would just distribute, collect like terms, and get x on one side, all the numbers on the other side, and then divide by whatever that factor is, right? So let's go through how I would solve this. I would multiply out. I'd get 12x minus 18 equals 2x plus 2. Then I move 2x to one side. I move 18 to the other side. I get 10x equals, that worked out nicely, equals 20. And then what I do, I divide both sides by 10, and I get x equals 2. Right? This is how I would solve this. This is like middle school algebra, right? So I think everyone in this class would be able to do that if I put it on the exam. But this, I'm telling you, is no different, okay? It's just weird-looking numbers, okay? It's just weird-looking numbers. So what do? The first step is, like in this problem, distribute. So I get 2 ln 5 of x, 2 ln 5 times x, right? That came from 2x times ln 5. I get minus 3 ln 5. That's here. And then equals, on the other side I have ln 3 times x plus ln 3, just distributed, right? And then what are we going to do? We are going to try to move everything with x over to this side and everything with numbers over to the other side. So after we do that, we have 2 ln 5 times x minus ln 3 times x equals 3 ln 5 plus ln 3. Now, there are two like terms, okay? these terms here are like terms. They both have a power of x, right? So when I add 2x plus 3x, how do I add these together? You just take the coefficients and add them. Yes, you just take the coefficients and add them. So what if it's ln of 2 and ln of 3? What are we going to do? We're just going to add those numbers, okay? We're just going to add those numbers together. When we do that, we get what's inside these parentheses, which is 2 ln 5 plus, minus ln 3, okay, times x. You okay with this so far? So then we have a number times x equals some other number. So I'm just going to divide both sides by whatever that number is. Okay, divide both sides by whatever that number is. Okay, and then we're done, right? That's what x is. It's not a very pretty way of writing it, but this is just a number. You could plug all these things into your calculator and figure out what this number is. Okay, so this is a really instructive example, I think. It kind of incorporates all of the different things which you might want to know about logarithms and also tests some of your algebraic ability. Any questions on this example? Yeah?
When you're you do 2 ln 5x minus ln 3x,
Mm-hmm.
and then you're going to step beneath that, where does the other x go? There's 2 x's on that side.
Yeah, good question. So what is the form of this? The form of this is like, you can imagine that this is like 2x minus, or let's make it 3x minus 2x. How would I resolve this with these numbers? The way I would do it is I would make the new coefficient whatever 3 minus 2 is times x, right? In this case, it would be 1x. So what I need to do when I'm combining like terms is I just take the coefficient and combine them and multiply with the common factor, right? So the only difference here is that usually when you do 3x minus 2x, you just do it in your head. You have forgotten the rule that says that this is how you do this. You just have gained a working familiarity with it, which there's nothing wrong with that. But it's good to remember, what do we do when these are integers? We just take the integers and subtract them, and that's our new coefficient. When there are other numbers, okay, like we could do something like 3.5x minus 2.3x, okay, what do? Again, we just subtract the coefficients. We would get 1.2x, right? Okay, but the thing is, you've done this subtraction, 3.5 minus 2.3 in your head because it's easy to do, right? But what about something like pi x minus ex? What do? Well, there's no easy way to write what is the number pi minus e. So I just write the number pi minus e like this. It makes maybe a little more sense with less letters, right? It's just I take the coefficients and subtract them. That's how I combine like terms. You've been doing it for a really long time. You just didn't know exactly like what is the formal process here, right? Does that answer your question?
Yeah, I didn't see the parentheses.
Oh, okay. Yeah. So there are parentheses around all of this. So I take the 2 here and just subtract them. All right. Any other questions on that one? Yep.
I don't know if this sounds stupid, but how did you get the 2 to move in front for the L in there, but then
Yeah, that's a good question. I rewrote this okay, I like to write numbers first. I like to write the number out front first, just personally. You could leave it like this if you want, but there is a good reason why I can rewrite it in this way. And that reason is that this is a number times x. I can do multiplication in any order that I want. Namely, you know the rule that says 3 times 5 is equal to 5 times 3, right? So multiplication can be done in whichever order I like. That is called commutativity, okay? So commutativity means I can do it in any order and get the same result. So I switch the order of multiplying this number with this number, and I just move this one over here to say I'm going to do this number times x. Does that answer your question?
Yeah, sorry. I had a second part to it too. Why did like the 5 go away and the parentheses of the second half of that and it got replaced?
This one?
Yeah.
This one went to the other side. I added this to both sides.
Okay.
So I added it to this side. These ones canceled, and I have one now on the right-hand side.
Okay, I see.
And I took this ln 3 times x, and I moved it over to this side by subtracting both sides by ln 3 of x.
Yeah, why did you do that?
Why did I do that? Can anybody answer that question? Why did I move ln 3 times x over to the left side and move ln 5 times 3 over to the right side? Yeah, Aaron?
Because you wanted the x's on one side.
Exactly. We wanted all of the things with x on one side so that we could combine them. And we wanted all of the numbers on the other side. Very good. Any other questions on this one? Okay, doesn't seem like there are, so I'm going to move on now. Okay, so then we had more equations, okay, things like where the x is trapped inside of a logarithm. How am I going to get it out of a logarithm? I'm going to use an exponential, right? So in this case, let's take a look at this one. When the x is trapped inside of a logarithm, we're going to get that logarithm by itself. And then we have what? We have this number is equal to this number. You can take both of those numbers and plug them into the function 2 to the x. And you will get the same result because the powers are the same. If you take 2 to a power and then 2 to that power again, of course you're going to get the same result because it's a function. Function, if you give it the same input, always going to give you the same output. There was a big kerfuffle about that at the start of class, right, with the vertical line tests and stuff. Okay, so you can plug both sides into this function, and then what happens? This is a process which looks like I'm going to take a number, I'm going to do something to that number, and then I'm going to immediately undo something. I'm just going to get back my original number. Okay, so that's, again, having this understanding of inverses for a to the x and log a of x is going to be crucial for the exam. Any questions on that one? All right, then let's look at this one. So, okay, what if it's more complicated like this? We're just going to put everything into a single logarithm, right? So when I have log 4 of this equals log 4 of this, you can, of course, take both sides to the 4th power, or rather take 4 to the power, which is this side, actually. We're plugging in this side into the function 4 to the x. We're plugging in this function into the... Jesus, I cannot speak. We are taking this side and plugging it into the function 4 to the x. All right. So that's all I want to say about logs and exponentials. Any questions about logs and exponentials that you want to talk about before we move on to the next section, which was, of course, angles and trig, in the next chapter?
Can you go back to that 4 plus 3 whatever, one of the x's and log? Right there.
This one? Yeah. Yeah, so what did we do? The first step was I want to get the x outside of this log. The x is currently wrapped up in the log and it's being multiplied by 3 and added to 4. So I'm going to get rid of the 4 first. Okay, that was the first step, was get rid of the 4. And then we got rid of the 3. And then we just had a log. I like having just a log because if I take just a log and use it as the power in 2 to something, it will go away. And then I'll just have x. Did you have any other questions on that one? No, you're good? All right. Thanks for your question. Any other questions about all of this logarithm and exponential stuff? Yeah.
Can you do one like we had on the quiz where it was like a function and it was log of a ratio of x minus 1 over x plus 2? Like an example of that one?
Yeah. Can you tell me what the exact problem was?
Yeah, f of x equals log parentheses x minus 1 over x plus 2. And finding like the domain of this problem.
Okay, so we need to find the domain of this function, right? Now, the way that you find the domain of a composition, if you remember, which you probably don't, but let me remind you. Let's see if I can find it. Was it in chapter 2? Maybe it was in chapter 1. Okay, come on. Where's chapter? There it is. Okay. It would have been like 1.8 or something. Here we go. The domain of a composition of functions. What did we need for the domain of a composition of functions? Well, we're trying to do f of g of x. So what do we need? We need x to be okay to plug into g. And furthermore, we need g of x, whatever we get as a result, needs to be okay to plug into f. Okay, so let's take something like 1 over the square root of x, right? First of all, we need to do square root of x, so we know that x needs to be bigger than or equal to 0. And we need the output to be of square root x to be okay to plug into 1 over x. Okay, so not only do I need x to be larger than or equal to 0 because we're doing a square root, I also need x to not be equal to 0. Because if x was equal to 0, well, fine, you can do the square root, but then you're going to have 1 over 0, and that's not okay. So there's a two-part process here. So let me use that to motivate this problem, which we were just talking about. Okay, so what do I need? I need, first and foremost, to be able to compute this number. If I can't compute that number, how are you going to do the log of it? So the first thing I need is I need this denominator to not be 0. So I need x should not be equal to -2. That's just a foregone conclusion, okay? Forget about doing the log. If x is equal to -2, you can't even figure out what this fraction is. Okay? So that's step 1. Then step 2 is, look, the output of this fraction must be an acceptable input for the log function. So, with that in mind, let's ask ourselves, what are acceptable inputs for log of x? What kind of numbers can I do logs of? Real numbers? Anything more specific than that? They need to be positive. Who said that? Good job. They need to be positive numbers. Strictly positive, right? The domain, this is a question about what is the domain of this function. The domain is 0 to infinity. So what do I need? I need the output, x minus 1 over x plus 2, needs to be a number which I can plug into the log function. It needs to be a number which I can plug into the log function. So I need to solve the following. I need whatever this number is, it needs to be positive. So I'm going to now solve this inequality. Okay, I'm going to solve this inequality. All right? Okay, so how am I going to solve that inequality? How do I do an inequality with a rational expression? Well, if we multiply both sides by x plus 2, this side's just going to still be 0, right? And so we would get just x minus 1 is larger than 0. But that's not equivalent, right? Because it's possible that the bottom could be negative when the top is positive, or vice versa, right? So we would be losing information by doing that. We would just say, well, forget about the denominator. But that we know that's not quite what we need to do, because that would be just ignoring part of the equation, right? Or the inequality. But there's a very specific method which I can use to solve rational inequalities. Yeah?
Well, we want to do two equations where it's x minus 1 is greater than 0 and then x plus 2 is greater than 0?
You're right in the sense that we care about when is the numerator positive and when is the denominator positive and when is the numerator positive versus denominator negative, and then all those other cases. We want to figure that out. But what's the specific method that we use to do that? You got it. It's the test point method. Okay? How do I use the test point method? I make a number line. And what am I going to put on my number line? I'm going to put 1 and negative 2, because 1 will make the numerator 0. That's when the numerator is going to change sign, is as we pass from less than 1 up to bigger than 1. So 1 is definitely going on here. And also, the denominator could change sign, and that would change the sign of this fraction. So I need that to also be on here. So I'm going to put negative 2 here. So there's 1 and negative 2. Okay, so that is our number line. What now must I do in order to do the test point method? Pick points from each section. What are our test points that you want to pick? I like those numbers. Negative 3, 0, and 2. I like those numbers because they're nice, whole, even numbers. I even got 0 in there, which is super easy to do. So let's see what happens. When I do 0 minus 1 over 0 plus 2, this is negative 1/2, which is less than 0. Therefore, the inequality is false in this region. Okay, false in that region. Let's try 2. When I plug in 2, I get 2 minus 1 over 2 plus 2, which is 1 over 4, which is positive. So I get a true statement for this region. How about negative 3? Negative 3 minus 1 over negative 3 plus 2 is going to be negative 4 divided by negative 1, which is 4, which is positive, so it's true. So I'm going to shade, okay? I'm going to shade with blue where the inequality is true. And how about at 1 and at negative 2? Am I going to put an open dot or a closed dot, and why? Open dot. Why? Exactly. It's not equal to. If you really want to know, just plug it in and see if it's true at 1. You would get 1 minus 1 over 1 plus 2. And we want to check whether it's greater than 0. Well, it's 0. Is 0 greater than 0? No. 0 is equal to 0. So I'm not going to shade. I'm going to put an open dot and an open dot. So what have I decided? I decided first and foremost, x cannot be negative 2. And second of all, in order for this fraction to be positive, so that I can do the log of it, I need to solve this inequality, which gives me a solution set of numbers which are less than negative 2 or bigger than 1. So at the end of the day, my domain is equal to all the numbers which are less than 2, negative 2, And I'm also going to throw in all the numbers which are bigger than 1. So notice that negative 2 is not included, so we're still in agreement with x is not equal to negative 2 here. And yeah, that's our domain. Any questions on this one? Okay, so domain of a composition. We need to, first of all, be able to do this. Second of all, whatever the output of that operation is, we need to be able to do the log of it, which means we get two inequalities, or we basically get two inequalities. First, x cannot be equal to negative 2. Second of all, whatever this number is must be positive. If you have two inequalities, then the solution set will be the intersection of both of them, where this is the set R with except negative 2, and we're going to intersect that with the sets negative infinity up to 2, negative 2, union 1 up to infinity. We take the intersection of these two sets. Well, negative 2 is already not in this set, so the intersection will just be the intersection of this set with R, which the intersection of this set with R is just itself. The intersection of any set with R is just itself. But maybe that's too much set theory. The point is, this must be true, and this must be true. You need to describe all of the numbers which make this true and this true. Any questions on that one? Okay, or any more questions on logs before we move on to chapter 4? Logs and exponentials. Okay, doesn't seem like there are, so I'm going to move on to the next chapter, which is chapter 4. Here it is. Okay, look how much I'm scrolling. We learned a lot. Okay, so it started off simple with just angles and their measurement. Okay, so positive angles we measure in the counterclockwise direction. Negative angles we measure in the clockwise direction. We call the first side the initial side and the final side the terminal side. And we call angles coterminal when they start and end on the same side. Don't necessarily have to go in the same direction. As long as they start on one side and they end on another side and those sides are the same, we call them coterminal. Okay? Standard position was just we put the initial side on the positive x-axis. So we measure counterclockwise for a positive angle or clockwise for a negative angle. All right, so then we talked about the measurements. So we had degrees, which 360 of them go all the way around. That tells you how much 1 degree is, because you need to go 1/360th of the way all the way around. Okay, and we have acute, obtuse, and right angles as well. And then we learned about radians. So what were radians? Radians were a different way of measuring angle, right? Just like how we have inches and meters, okay? We have degrees and radians. And how much is a radian? Well, for inches and meters, it's just someone decided one day that this is how much a meter is, and then we all agreed that that's a meter from then on. For radians, it's actually a lot better than that. We have a good reason to know what is a radian. A radian is the angle measurement such that if you put it in the unit circle, you achieve a pizza crust length which is equal to that angle, right? So pi radians looks like this angle. The reason we call this angle pi is because if you were to walk along the exterior of this pizza on the crust, you would walk exactly pi units or pi miles or whatever in order to get to this side. Okay, so that's radians. How do we convert? Okay, well, what you need to do to convert is multiply by either 180 over pi if we're going from radians to degrees, or if we're going from degrees to radians, we need to multiply by the opposite of that, or the reciprocal of that, which would be pi over 180. Okay, so that's degrees and radians. Okay, so this is a very important concept which I'll talk about now, which is coterminal angles, okay? Why is this important? This is important because when we want to do sine and cosine, okay, or any trig function, we like the angle to be an angle which is between 0 and 2 pi, because that's easy for my peanut brain to visualize, right? If the angle is like 1,000,000,005 degrees, like I don't know what that looks like. So I got to convert it to an angle which is coterminal, which is between 0 and 2 pi, right? Or 0 and 360 degrees. So I do that by either adding or subtracting multiples of 2 pi, or adding or subtracting multiples of 360. Okay, that's how we do that. So for example, here we have the angle 19 pi over 4. It's really to go around this many times and end up here, but it's the same end result as if I were to just do 3 pi over 4. So how do I get that? I just take this number and I subtract 2 pi. And if I'm between 0 and 2 pi after that, I'm done. If not, I'm going to subtract 2 pi again, and I'm going to subtract 2 pi again. I'm going to do that however many times I need to do it in order to achieve a number like 3 pi over 4, which is between 0 and 2 pi. I only like to go part of the way around the unit circle. I don't like to go around 5 times and then part of the way. That's confusing to me. Okay, so that's what we do when we need to find coterminal angles. Any questions on that? All right, then what else did we learn? We also learned about the trig functions. Okay, first of all, we can never ever forget that the unit circle has various properties. Namely, its equation is x squared plus y squared equals to 1. Radius is 1. Circumference is 2 pi. Area is, well, you don't really need to worry about area. Okay, but the crucial thing to understand about the unit circle is that for any point on the unit circle, I can always draw an inscribed triangle, which is a right triangle. And furthermore, the hypotenuse of that triangle will always have length 1. Why will the hypotenuse of my triangle always have length 1? Because it is a radius of the unit circle. It goes from the center of the unit circle to the outside of the unit circle. The whole point of this circle is it's the collection of points which are exactly 1 unit away from the center. So I know this point is 1 unit away from this one. And likewise, I know this point is 1 unit away from the center as well. And all the points are 1 unit away from the center. So that's the unit circle. We also learned about special right triangles, okay? What you need to know about special right triangles is how to go from one side to the other and how to go from the other side to the one, okay? Namely, for 45, 45, 90s, we're going to go from the short leg to the short leg. They're going to be the same. But to go from the short leg to the long leg, we would multiply by the square root of 2. However, more often than not, when we're in the unit circle, we don't want to go from the short leg to the long leg. We want to go from the long leg to the short leg. And we do that by doing the opposite of multiplying by the square root of 2. Namely, we divide by the square root of 2. So that's 45, 45, 90s. There's a similar process for 30, 60, 90 triangles, which we need to know how to go between. So, next up we learned about how you can visualize the input of the trigonometric functions. Well, you can visualize it in 2 ways. You can say, well, I'm going to take the angle as my input. Or you can say, if you're using radians, you can say, I'm going to use the arc length on the unit circle. I'm going to walk around however much, and then I'm going to see what point I'm at. Okay, you can do that as well, if you're using radians. So what do the trig functions do? I want to put this as succinctly as possible. You take the input, which is always an angle. You put the angle inside the unit circle, and you go to the point. And the trig function will give you something to do with the coordinates of that point, okay? So if it's sine, it's going to give you the y-coordinate of that point. If it's cosine, it's going to give you the x-coordinate of that point. Tangent, you get the ratio so on and so forth. Okay? So these are our trigonometric functions. Really, all you actually need to remember is sine, cosine, and tangent, because cosecant, secant, and cotangent are just reciprocals of those three. Okay? So these are the 6 trigonometric functions which give us the coordinates or something to do with the coordinates of the associated point. So what do I do when I want to compute something like this? Well, the first thing I need to do is put the angle inside the unit circle. And what am I going to do if this angle is bigger than 2 pi? I'm going to incrementally subtract 2 pi until it's less than 2 pi. What if this angle is negative? Then what? I'm going to add 2 pi until it's positive and between 0 and 2 pi. Okay? Then I'm going to put the angle in the unit circle. I'm going to go to the point. I'm going to complete this triangle, and I'm going to find the coordinates of the point on the unit circle by using the theory of 45, 45, 90 triangles or 30, 60, 90 triangles. So I always know one side length is 1, so I just need to figure out what the other side lengths are using 45, 45, 90 or 30, 60, 90 triangle theory. Okay, so that's how I would do that. And then, of course, if you're doing cosine or sine or whatever, then you need to take the relevant coordinate. So for cosine, it always gives us the x-coordinate of the point. So that's what cosine of pi over 4 is. It's the x-coordinate of the point on the unit circle, which the angle pi over 4 points towards. For sine, it would give us this y value. For tangent, what would tangent of pi over 4 be? 1, right? Because you take the y-coordinate, divide it by the x-coordinate. You take one number, divide it by itself, you get 1, always. Okay, so that's cosine, and that's how we do trig functions, right? Okay, so here's a nice little graphic. I don't recommend that you memorize this unless you have superhuman memorization capabilities like Chris. Then you can do that. So what I want you to remember is, look, for any of these points, you can draw a triangle. And this triangle will be a 30, 60, 90 triangle or a 45, 45, 90 triangle. Okay? Another thing I want to be a little bit careful about is, look, if this is a 30, 60, 90 triangle, I know that the side lengths are 1, 1/2, and the square root of 3 over 2, but I have to be a little bit careful when I give the coordinates of this point, because even though this length is square root 3 over 2, what is the y value? Negative square root 3 over 2. So don't forget which quadrant you're in. That also is going to affect what are the coordinates of your point. Any questions so far on trig? All right, then I'm going to move on to section 4.3, where we learned about the signs of trigonometric functions. So never forget this acronym ASTC, or All Students Take Calculus. It goes in the order of 1, 2, 3, 4, i.e. the quadrants of the coordinate plane. And they tell us when are the trig functions going to be positive or negative. And it only tells us this for sine, cosine, and tangent. But that, of course, tells us the other ones too, right? Because the reciprocal of a positive number is positive still. The reciprocal of a negative number is negative still. So all trig functions are positive in the first quadrant, just sine, because look, this point has a positive y-coordinate, but a negative x-coordinate. So that's why sine is going to be the only positive one. Down here, we have negative, negative. That's the reason tangent is less than 0, because a negative divided by a negative will be a positive. And then we have cosine is the only positive one because the x-coordinate of this point is positive, but the y-coordinate is negative. Okay, so that's ASTC. So, yes. We also have the periodicity of trigonometric functions, namely sine of theta is going to be equal to sine of theta plus 2 pi n. Add any multiple. Why is it going to be the same? It's going to be the same because they're going to point at the same point on the unit circle, and sine just cares about the y-coordinate of that point. If it's the same point, the y-coordinate is the same, the output of the sine function will be the same. Okay, so let's see more stuff. This is just more review. Pythagorean identities. Oh, okay, Pythagorean identities. Why is sine squared t plus cosine squared t equal to 1? Of course it is equal to 1. It must be 1 because this is a triangle. And triangles have the Pythagorean theorem if they're a right triangle. And this is a right triangle, so we can add the side lengths and get, if you square the side lengths, add them together, you get the square of the hypotenuse, which is 1. So 1 squared is 1. So that's why that identity is true. And then if you take this identity and either divide by cosine squared t, which is easy to remember because it's right here in the formula, or you divide by sine squared t. If you divide everything by that, you will get the relevant Pythagorean identities for tangent and secant and cotangent and cosecant. Oh yeah, crucial thing, the t here, the angle t, has to be the same in both of them for that to be true. Okay, so, oh yes, so even an oddness of the trig functions. Well, we found that sine is an odd function because when you flip the input, the output also changes, flips, right? Whereas cosine, the output of alpha versus minus alpha is going to be the same for both of them. That's because cosine is an even function. You can see that because the graph of cosine is symmetric about the y-axis. The graph of sine, on the other hand, is symmetric about the origin, right? About the origin. So it looks like this, right? That's symmetric about the origin, i.e. odd function. Tangent is also odd because you take an odd divided by an even, you still get odd for functions. Okay, so that's odd and evenness. Then we learned about the graphs of sine and cosine, right? I know I'm going fast here, but I just want to remind you all of the things that are here so that hopefully you can identify for yourself which are the things that you want to study. So the graphs of sine and cosine, we need to know the domain and range. The domain is always r for sine and cosine, and the range will always be -1 to 1. Okay, so what do the graphs look like? They look like this. How do we get the graph? We take the angle, we put it inside the unit circle, we check the coordinates of this point, and for sine, we take the y-coordinate and we make that to be the height of the function for that given input. So the inputs go left to right on this graph, but the way you visualize the inputs, the corresponding inputs on the unit circle is the angle is getting larger and larger and larger, okay? The angle is getting larger and larger because the inputs here are the angle which we inscribe. And after we go 2 pi, the function is going to just repeat. Why? Because this angle points at the same point as does the angle where we go around 2 pi and then again that little bit, right? So that's sine and cosine. The graph of tangent, of course, is given by these asymptotic behavior where the denominator is going to 0 as we go up to pi over 2. So we needed to check, are we going to plus infinity or minus infinity using limits? And then finally, we learned about the inverse trigonometric functions. Oh, sorry, I forgot about stretching vertically and stretching horizontally. Okay, so we are going to change the amplitude or the period of the sine and cosine function according to a vertical stretch or shrink or a horizontal stretch or shrink. And what you need to remember most of all probably is that when we have a number inside which is bigger than 1, that's going to cause us to have a horizontal compression, okay? So on the outside, if the number is bigger than 1, we get a stretch. But if the number is on the inside and it's bigger than 1, we're going to have a compression in the horizontal direction, as you can see here. Okay, then we learned about the graphs of other trig functions. I'm going to tell you now I'm not putting graphs of other trig functions on the exam. So you don't need to know the graphs of them. But you do need to know generally how to compute cosecant, secant, and cotangent. But they look like that for your reference. I'll skip that for now. Finally, the inverse trig problems, right? We need to know what is the angle which produces a given output for the sine function. In order to do that, I have to restrict my vision to just the right half of the unit circle for sine, or just the top half of the unit circle for cosine. So the way we did those problems was as follows. You take whatever is the input of the inverse trig function, and you make that the height or the width or the ratio of the height to the width of the point on the unit circle here. Okay, so negative square root 2 over 2 became the height of this point since I'm doing inverse sine. And since I'm doing inverse sine, I'm not going to worry about the left half of the unit circle. I'm going to just forget about it. And I'm going to only think about what's happening on the right half of the unit circle, where the angle is going to be between negative pi over 2 and pi over 2. So in this case, the angle I got was negative pi over 4, because that is the angle which is shown right here, which produces a point on the unit circle whose height is negative square root 2 over 2. Okay, and we saw similar things for the other trig functions. Okay, so that's all we did. Not too much to study, right? No, that took a while, right? So you're probably noticing, wow, there's kind of a lot of content on this exam, and also it's kind of the hardest content that we've learned in our class. So, not to scare you, I just want you to be aware that this is probably going to be the harder exam of the three. So, with that, are there any questions on specific topics that you'd like me to dive in a little bit deeper or do an example on? Yeah, Randall? Yes, inverse of tangent. That's a good question. Let's do a problem like this. Let's do tangent inverse of the square root of 3. Okay, this is a really challenging problem to do. The reason I think this is a really challenging problem to do is the following. I feel like this vertical line is not straight. There we go. Okay, we have our circle here. Nice. So why is this really challenging to do? Because, first of all, when I'm doing tangent inverse, I'm going to restrict my vision. How am I going to restrict my vision? I'm going to restrict to the right side. And actually, I'm going to go between negative pi over 2 and pi over 2, and I'm not going to include negative pi over 2 or pi over 2. Why not? Because? Yeah, it's undefined, or it has a vertical asymptote at those points, right? Tangent, you can't do tangent of pi over 2. It's 1 over 0, which is not defined. Okay, so I'm going to restrict my vision to the right half of the unit circle, and I'm going to look for a point such that what is true? I want the output of the tangent function to be square root of 3. So I know tangent of theta is the square root of 3, yes? So I know that y divided by x, it's a point on the unit circle. First of all, I know I'm in the first quadrant, don't I? Because this is a positive number. Tangent, if you remember ASTC, only takes positive values in the first quadrant and the third quadrant. So I know that I'm not worried about this fourth quadrant at all. Okay, so we're not going to be in this quadrant. So I know that my point is going to live in the first quadrant since tangent is positive. And I know y divided by x is going to be equal to the square root of 3. Okay, it's going to be equal to the square root of 3. Another way that you could say that would be to say the following. Y is equal to the square root of 3 times x. y is equal to the square root of 3 times x. So what do I know? I know there's going to be a triangle living here. And I know something. I know that this side length, the y, is square root of 3 times whatever the side length here is. What kind of triangle am I in if I move from the short leg to the medium leg by multiplying with the square root of 3?
30, 69.
It must be a 30, 60, 90 triangle. Are we okay with that? So this is some kind of heavy reasoning here, actually. It's tricky. You need to have an understanding of what is tangent. It's the ratio between y and x. You can multiply both sides by x and figure out, basically, how do I get y if I know what x is? Or how do I get x if I know what y is? Right? So, this side length is bigger than x, right? Y is bigger than x because I multiply by a number bigger than 1. So, what must the coordinates of this point be?
1/2, square root 3 over 2.
Good, 1/2 square root 3 over 2. So, that is going to inform us of the interior angles in this triangle. I know that this one down here is 90. And this side length, x, is 1/2. What angle is 1/2 across from? The 30. The shortest side is across from the shortest angle, so I know this angle is 30. Which tells me what is this angle going to be? 60. And what is tangent inverse's job? It's to go to the point on the unit circle such that the ratio between the y and the x is square root of 3, and then do what? What should the output be? The output should be the angle in radians, which produces a point whose y value divided by its x value is square root of 3. Which means the output of this is going to be what? Good, pi over 3. That's 60 degrees in radians. Yeah. Okay, any questions on that one? Yeah.
Can we just go over again, like, how you know which one is 30 and which one is 60?
Sure. Well, I first derived the following. I know that tangent theta is square root of 3 because I'm doing tangent inverse of square root of 3, which means I'm looking for the angle such that if I do tan of theta, I get that as the output of the tangent function. So I'm looking for an angle theta, which would point at a point on the unit circle whose coordinates obey this equation. Are you okay so far? Okay, so once I have this equation, I can determine that the height of this point, which you can visualize as the y-coordinate, or you can visualize as, quite literally, this length here, right? This length here is this much more times this side length. So I immediately know that I have a 30, 60, 90 triangle because the side lengths are obeying this 30, 60, 90 ratio. So that's how I determined that this was a 30, 60, 90 triangle. Now, that doesn't tell us which angle goes where, right? Which I think is part of your question, right? It only tells us that we have a 30, 60, 90 triangle, but is it one that looks like this or is it one that looks like this? That's a question mark, right? So we determine it in the following way. We know that x and y are going to be the short and medium side, respectively, yes? And we can tell from this equation that y is bigger than x. Do you agree with that? Y is bigger than x because we're multiplying x by a number bigger than 1, and we get our y. So I know that the way this triangle works is that this is going to be the short side, this is going to be the medium side, and this is going to be the long side. Yes? And I know that the shortest side in a 30, 60, 90 triangle is the 1/2. So I know that this is 1/2, and I know that this is square root 3 over 2. So that gives me these coordinates of this point. And then what? The shortest side will be across from the smallest angle. And then the medium side will be across from the medium angle. So that's how I figured out where the 30 and the 60 go. Does that answer your question? Yeah, no problem. That's a great question. It's tricky. I think tangent inverse is probably the hardest inverse function to do. Yeah.
How did you know that it was like pi over 3?
Because I knew that this was 60 degrees, and I have memorized that 60 degrees is pi over 3. But what would you do if you didn't have that memorized? How would I convert 60 degrees to radians? You would multiply by pi over 180, okay? And then cancel, 60 goes into 180 3 times. So we would get pi over 3. Make sense? Any other questions on this tangent inverse problem? My final comment on this would be, look, tangent inverse is the hardest because when you're doing sine inverse, you automatically get the y coordinate. When you're doing cosine inverse, you automatically get the x coordinate. Here it's not so simple. They tell us the ratio between y and x. So we have to infer from this, what are the coordinates of this point going to be? And then we have to figure out what kind of triangle this is, what are the interior angles going to be, and so on and so forth. Okay, next question. What's something else that you all want to discuss? Yeah.
Can we go over an inverse tan with a tangent side of that as well?
Let's save that for office hours. What I want to do now is something which was on the quiz, which didn't go over as well as I had hoped, it was something like cosine of negative 33 pi over 2, or something like that, right? Okay. How do I do something like this? Someone help me out. Okay, yeah, make a unit circle. That's a good first step. And what next?
Don't you want to add or subtract between?
Yes. This angle is hard for me to visualize, okay? It's hard for me to visualize. So I'm going to add multiples of 2 pi until I get something which is between 0 and 2 pi. So you can do that in one of 2 ways. You can literally go, and many people did this, you can literally say, okay, plus 4 pi over 2, and then what do we get? That's negative 29 pi over 2. And then, I'm just going to keep doing this, plus 4 pi over 2, and I'd get negative 25 pi over 2, right? And then plus 4 pi over 2 again. You can do this if you want. It's going to take you quite a few. Or you can visualize immediately how many times you're going to need to do it by thinking, well, look, 33 is 3 less than 36 pi over 2. And 36 pi over 2 would be 18 pi, which is a multiple of 2 pi. And that's what I need to add to this in order to get something which is between 0 and 2 pi. So if I take negative 33 pi over 2 and I add to that 36 pi over 2, what do I get? I get 3 pi over 2. Okay? I get 3 pi over 2. Is that clear how we did that? So if you want to do it iteratively, fine, but it's kind of annoying, and you might make a mistake. This way, you can visualize, look, another pitfall that somebody might fall into is to say, well, I'm going to add 34 pi over 2. Why can I not do this? This would give us an angle which is between 0 and 2 pi. Yep.
That's 17 pi.
Yeah.
That's not like a multiple of 2.
This is 17 pi. Okay, that's going to not be a multiple of 2 pi. Even though they're even numbers, take an even number divided by an even number, you could get odd, right? So 34 pi over 2 is not what I want to add, because that would be not a coterminal angle. It would actually give us the angle which is opposite. Okay? It would actually give us the angle which is opposite. So quite literally giving us the worst possible answer. So we want negative 33 pi plus 36 pi over 2, because that's a multiple of 2 pi. So then what? I know that this, cosine of this, is equal to cosine of 3 pi over 2. And I'm just going to figure out what this is, because this I can easily visualize. 3 pi over 2 goes to here. And the point, the corresponding point is the point 0, comma, negative 1. And so cosine of 3 pi over 2 is 0. And therefore cosine of negative 33 pi over 2. What does negative 33 pi over 2 look like as an angle? Well, you go around like 9 times and then end up back here. All right, we'll stop there for today. In office hours, we're going to do a butt ton of example problems, okay? So come to office hours, or if you can't make it, I highly recommend watching the YouTube video.